Alright, we're going to conclude section 14.6 in this video, and I'm going to do another example from 14.6. We're on page 951, and we're going to look at number 19, which says in exercises 15 through 21, find the volume V of the region. So, and we are given the solid region bounded above by the upper nape of the cone, x squared plus y squared equals z squared, on the sides by the cylinder, x squared plus y squared equals 4, and below by the xy plane. So here our top that we're given is x squared plus y squared equals z squared. But they told us it was the upper nape of that cone, so that's just going to be z equals the square root of x squared plus y squared. And our bottom was the xy plane. Z equals 0, and our size, the cylinder, x squared plus y squared equals 4. And I'm going to go ahead and sketch this in 3 dimensions so we kind of have an idea of what's going on here and some information we can figure out from our sketch. So first I'm just going to sketch this, I'll sketch the cone. So we have our cone, that's the upper nape of the cone. Actually, I should have sketched the cylinder first, but so we have our cone. And the cone is going to go on forever, but if there's a cylinder, then that cylinder is what's cutting the cone off. So we'll sketch the cylinder. It's going to cut off that cone. So, and then I stop the cylinder at the XY plane because our bottom is z equals 0. So our top is the cone. So really, I'm going to sketch this. I'm going to shade this, but I'm not going to actually shade the whole thing in. So it really would, I would shade in the entire cylinder, and then it would be hollowed out. The inside would be hollowed out by the cone. So you could, let's say, no, I don't want to be, that'll be misleading if I shade that way. So that would be our region, but there's a hollowed out, so don't shade the top to indicate that there's a hollow portion on the inside where the cone is. So the top is the cone, the bottom is the XY plane, and the sides are the cylinder. So notice from this, we can quickly see that our theta is going to vary from 0 to 2 pi. Now our rho and our phi aren't as apparent. Those are going to vary between. We can see our phi is going to stop. So our phi will never be 0 because that would be the x-axis. So our phi is going to start right here, and it's going to go all the way down to the xy plane. And the xy plane is phi equals pi over 2. So we can see our upper bound on phi is pi over 2 from our image that we have here. Our lower bound on phi, we just have to figure out what angle this is between the cone and the positive z-axis. We've seen that though in a previous example. We'll do it again though. So let's go through and use our equations and figure out, well, let's go ahead and write down what theta is because we know theta varies between 0 and 2 pi. We could see that. So now let's take our top, which is z equals the square root of x squared plus y squared. And we actually had this exact same cone in our last example, but we'll go through the steps again. So this is rho cosine phi equals rho sine phi. So we pull everything over to the left. That's rho cosine phi minus rho sine phi equals 0. We factor out our rho. Which that tells us rho equals 0, or cosine of phi equals sine of phi, which tells us phi equals pi over 4. All right, so we got two things from there. Rho equals 0. The smallest our rho ever is 0 when we're right here, and it varies out to right there. It varies out to whatever this distance is. But notice the rho is going to depend on what your phi is. So we know I can tell the rho is going to be a function of phi because I have this distance rho right there, whatever that is, and then I have that distance, which is shorter than that one. I have that distance. So it depends on what our rho, whatever we get, is going to depend on phi. So of course it's 0 right there, and it's going to go out to whatever that line is. That's going to govern our rho. So let's now figure it out algebraically. So we see that's the cylinder is going to govern our rho. So probably going to get that from the cylinder equation. So we have x squared plus y squared equals 4. So now we're going to take our conversion formulas, and remember the square root of x squared plus y squared is rho sine phi. So that means this is rho squared sine squared phi. So rho squared sine squared phi equals 4. We take the square root of both sides here, and because phi is always between, just in general, it's always between 0 and pi. So our phi is always going to be something between 0 and pi. That means sine of phi is always positive, and rho is always greater than or equal to 0, or sine is always greater than or equal to 0. And rho is always greater than or equal to 0. So when we take the square root of both sides, we're not going to get a plus or minus. We're just going to get rho sine phi equals 2. Because both of these things always have to be greater than or equal to 0 for the bounds that we have in spherical coordinates on phi. All right, so now remember we're looking for rho because we already figured out information about phi. So we solve this for rho, and we get rho equals 2 over sine phi, and 1 over sine is the same as cosecant, so we get this equals 2 times cosecant of phi. So now we have our theta varies between 0 and 2 pi. Our rho is going to go between 0 and 2 cosecant phi, and our phi is going to go between pi over 4 right there and all the way, and we know this is the pi over 4 part because it came from the cone, and it's going to go all the way down to phi equals pi over 2, which is the xy plane. So now we can set up our integral. Let me write the other stuff up here. So rho was between 0 and 2 cosecant of phi, and phi is between 0, oh no, I'm lying, between pi over 4, excuse me, and pi over 2. This is the xy plane right here. And you also, to get this, could certainly use the bottom equation, which we didn't go through and do. We used our picture, but if you can use the bottom equation, just do rho cosine phi is equal to 0, and then at the bottom we know our rho. So I'll just go ahead and do it since I'm talking about it. So let's do it down here where we did everything else. So it's all in one place together. So we had z equals 0 gives us that rho cosine phi equals 0. And you don't, if you figured out stuff from your picture, you don't have to do the picture and the algebra. I tend to do both of them just so you can see both ways, but there's no need to do both. You do whichever one works for you, and is going to make sure that you ensure that you get the integral set up correctly. So now when z equals 0, our rho is not 4. I said 4, but it's actually 2. So, all right, so it's 2. So that's going to be 2 cosine phi equals 0, or cosine phi equals 0. Cosine phi equals 0, which tells us that our phi, and remember our restriction on phi has to be something between 0 and pi over 2, and that tells us our phi has to be equal to pi over 2. So if you're not comfortable with the pictures, notice we used all of our equations and found everything we needed from just using the equations alone. Rho, with the exception of theta, that was the only thing. So that is going to involve some level of visualization, but given you know you have a cylinder, that will help with that aspect. All right, so now we can go ahead and set up our iterated integral. All right, so our theta went from 0 to 2 pi. Our phi went from pi over 4 to pi over 2. And our rho went from 0 up to 2 cosecant phi. Our integrand, we're finding volume, so our integrand is 1. But then we have the parameter that is always included when you're using spherical coordinates, which is rho squared sine phi. These are rhos. So d rho, these are phis, d phi, and those are thetas. D theta. So notice here you cannot split this up into a product of 3 single integrals as I did in the previous example, because there is these bounds here are not all constants. All of your bounds have to be constants. All right, so that concludes section 14.6. 14.7 is not covered in this course, so the next section we'll cover is 14.8.